The Friedel-Crafts acylation and alkylation reactions are special cases, well, not all that special, of the electrophilic aromatic substitution reaction. So let's go back to what is the principle of electrophilic aromatic substitution. It's to have an electrophile. So in the case of Friedel-Crafts, that'll be a cation, a carbocation, that will react with an aromatic pi system. So consider first, if we recall that an electrophilic aromatic substitution uses the pi bonds as a nucleophile on a benzene ring, right? There's a cloud of electrons there that go out and add an electrophile. So we just need to make a good electrophile. So the electrophiles that we've used in the past, something with a plus charge on it. So we activated a halogen to add, or the nitro, or a sulfate. But in the case of the Friedel-Crafts, it will be a carbocation. So there's a few things about the carbocation, the Friedel-Crafts alkylation reaction, that we should keep in mind. First of all, Friedel-Crafts, both of these, will only work if you have a benzene with a halide, benzene with a donating group. So this is an activated ring, this is neutral, and this is just barely deactivated by the pull on the hydrogens. But they're all ortho-pair directing, right? Because they're active enough. But it will not work on a withdrawing group, so a strongly deactivated ring. So that means anything that's something like this would be a withdrawing group on a benzene ring. So that will not do a Friedel-Crafts. No Friedel-Crafts. Okay? We also will have alkylation, the Friedel-Crafts alkylation, be subject to rearrangements anytime you can get a better carbocation. So C+ rearrangements. And also the product of a Friedel-Crafts alkylation is more active than the starting material. So polyalkylation is likely. But let's consider a Friedel-Crafts alkylation just to get started. So let's think, maybe I want to add to a benzene ring, let's say benzene, and I can form a carbocation with this, CH3CCl. There's our leaving group, CH3, CH3, ooh, T-butyl. So if I activate this with AlCl3, aluminum trichloride or aluminum chloride, I will create the carbocation that's needed. So my intermediate, let me just draw a longer line there, will be this carbocation right here. So that's a fairly stable carbocation. And so it didn't just happen on its own. We added a catalyst, right, to encourage the formation of that carbocation. And then my benzene that's hanging around will add that carbocation. So essentially anything that forms a reliably stable carbocation will get us some sort of Friedel-Crafts reaction. We've noticed that they're not brilliant reactions, 28%, 31%. We even got up to 65 or so at one point. But what we get in this addition will be the carbocation has added. I still have an H on there. And then I should have a carbocation on the carbon next door to where I added, right? So it's electrons here that were used to form the bond here. And so they were removed from the carbon here, and that's why we have a plus charge. Okay? Now, of course, as per normal, we can move the electrons around and draw new resonance structures. So I'll put the T-butyl group on there, the H, and an H that's still there. And now I'm going to have a double bond here and a plus charge here with its H still present. And I can move these electrons around. These are all stabilizing forces that allow this reaction to go forward. And there's another plus charge. So this is the sigma complex that is the intermediate in the process of a Friedel-Crafts reaction. So we've seen this in a number of cases. The Friedel-Crafts alkylation and acylation are no different. It's just a matter of what is it we're actually putting on there? A carbon-carbon bond formation. And so that's the key thing about a Friedel-Crafts. Whoops. Friedel-Crafts is carbon-carbon bond formation. So the other ones were some other functional group, right? But a carbon-carbon bond formation is increasing the size of your molecule, and that's why these are particularly interesting. So that's Friedel-Crafts alkylation. Alkylation because I'm adding an alkyl group, right? That's the carbon-carbon bond formation. An alkyl group will be some carbon containing thing that is forming a bond to another carbon-carbon bond. So now let's consider acylation. So now I don't have an alkyl group, which is just alkane, right? Alkanal. Instead, I have an acyl group, acylation. So an acyl group is that carbonyl. So we had a way in our textbook, in our lecture, to create this carbocation. Something like this, right? That was one form. And so now we can add that to our benzene ring in the same way we added the other alkyl groups, only this now will be an acyl group instead. So it's all the same. We have a plus charge here. You can even write those same kind of resonance forms for the sigma complex. But this time, instead of forming a carbon to a carbon alkane group, you're forming a carbon to a carbonyl group, right? That's a carbonyl group right there. And so that actually is a little bit different because in this reaction, the alkylation, polyalkylation is likely because now I have an activated ring. So I can keep adding that carbocation more polyalkylation. So that means multiple spots may have this T-butyl group on it, right? But in the case of a carbonyl, that's actually a deactivated ring now, right? Once it moves on from the sigma complex to the product, it's a deactivated ring. And so that means it will not react further, whereas what we did here was activate the ring. And so that's the difference between alkylation and acylation. This one tends to give us better results, more reliable products that we can go on and reduce to the alkyl group if that's what we wanted to get.